Welcome to Empowered Learning. This is part 4 in the video series for evaluating improper integrals. So in this video, we are going to talk about the direct comparison theorem and the limit comparison theorem. So both of these theorems really give us a way of being able to figure out if an improper integral converges or not without us actually having to evaluate the improper integral itself. And so basically what it does is it will allow us to be able to compare the improper integral that we're dealing with something else that's relatively close to it that we already know either converges or diverges. Okay? And so the direct comparison theorem is a theorem that we will deal with first because it gives us a very direct way of knowing whether the improper integral that we're dealing with actually does converge or not. Okay? If the integral that we are dealing with does not meet the two conditions of the direct comparison theorem, then we will have to move on to the limit comparison theorem and use those conditions to be able to figure out if the corresponding improper integral that we're dealing with is convergent or divergent. So in a nutshell, that is what these two theorems are all about. So I'm going to go ahead and skip down to what the actual direct comparison theorem for improper integrals is for. So I'm going to take some time to translate what we're looking at here because there's a lot of information here, but once we kind of get it all in, we'll be able to summarize it. So first, we want to suppose that we have two functions, f and g, and they are both continuous functions. Okay. Now, we are considering both f and g to be continuous functions such that they meet either one of these two conditions. Okay, so condition number one is that our function f and our function g are both functions that lie above or on the x-axis. Also, we know that our function f is bigger than our function g. So what we're going to do here in this instance, I'm not sure why that's happening, but let's fix it. So what we're going to do in this instance here is name this f of x. We're going to call this the big function, and we're going to call g of x the little function, just to kind of keep from having to say f of x and g of x all the time. Okay. So we have these two functions, the big function, the little function. Both of them lie above or on the x-axis for all values of x that are a or larger. And we know that one of these two functions may have a horizontal asymptote as x approaches 0. Okay, and let's make that a little bit smaller so that we can see that. Now that's condition one. Condition two, we have our big function and our little function again. So we got both the big function and the little function here are able to lie either above or below the x-axis, meaning that both can lie above the x-axis, both can lie below the x-axis. You can have one lying above, one lying below. Okay, so any one of those scenarios is fine. So if we have a situation where basically the sign of the y values of f and g do not matter, then we'll know that one of these functions at least has a vertical asymptote or some other type of jump discontinuity that makes the function's y value switch signs around it. So that's kind of the basic idea around condition number two. I just put vertical asymptote here because it was the easiest thing to try to quantify in your mind what that would look like, because of the fact that with vertical asymptotes, we know that we have some vertical asymptotes where the function's y values do not change signs across the vertical asymptote, and sometimes it does. Okay. Of course, that can also happen for jump discontinuities too, but I had to get into explaining all the different types, and didn't really want to do that here. All right, so we know that our big function and our little function can pretty much lie anywhere. At least one of these functions will have to have a vertical asymptote on this interval, where, again, the absolute value of the big function will be larger than the absolute value of the little function. Okay. So the direct comparison theorem basically says, hey, if we have a big function and a little function that meets at least one of these two conditions, then if our integral for the big function is convergent, then that means that the definite integral for the little function is going to follow suit and also be convergent. Okay. We also see that if our little function, if the integral for that little function is divergent, then we know that the definite integral of the bigger function is going to follow suit and will also be divergent. Okay. So to put it real simple, to translate this, if we have functions that are continuous, that may either have a horizontal asymptote or a vertical asymptote somewhere in the interval of x being greater than or equal to a, then we know that if the improper integral of the big function converges, then the improper integral of the little one converges. If the improper integral of the little one diverges, then it means that the improper integral of the big one will also diverge. Okay. And so that is essentially what the comparison theorem, the direct comparison theorem, is talking about. Okay. Now, notice here that we've only dealt with 2 of the 4 possible conditions here. Okay. And so I'm going to list those. So for the direct comparison theorem, why does it do this? So for the direct comparison theorem, we've only dealt with, I'm going to put it like this, integral big function converge, and integral of little function diverge. So we've only dealt with those 2 situations here. What we haven't dealt with is what happens when the integral of the big function diverges, and what happens when the integral of the little function converges. So we don't know what happens there. Okay. Now, it turns out that for these 2 situations here, this is what the limit comparison theorem is for, to be able to give us a way to figure out whether an improper integral is going to converge or not, based upon these situations here. Okay. So here I'm just going to say the limit comparison theorem, which we're going to study next, is going to help us handle those 2 situations. All right, so let's move to it. So now let's look at the limit comparison theorem. So we're assuming here that whenever we use the limit comparison theorem, that we've already tried a direct comparison theorem. Okay. Now, in actuality, you could actually just use the limit comparison theorem to start off with, without going through the direct comparison theorem. But it actually makes more sense to actually look at the direct comparison theorem first, okay? Because of the fact that if you're doing the limit comparison theorem and you can use direct comparison theorem, you're going to do more work than what's necessary, okay? All right, so looking here, let me switch colors here. We see that for the limit comparison theorem, we're again considering that our functions f and g are continuous on this half open interval here. We're still considering that our functions f and g are still both lying above or on the x-axis. But here we haven't really specified which one is the bigger function and which one is the little function, okay? And that doesn't really matter for the limit comparison theorem, okay? Now, it says that if we have two functions that are continuous on this half open interval, and if both functions lie strictly above or on the x-axis, and this other condition, if the limit of the quotient of those two functions as x approaches infinity equals to L, where L is some positive real number, then either the improper integral for both the big function and the little function, either they both converge or they both diverge, okay? Now, what does this mean? So let's dig a little deeper into this. We have two functions that are continuous on this half open interval. And here, both of those functions are assumed to be ones that lie strictly above or on the x-axis. This limit here, what it's actually trying to do is, in a way, compare the growth of f of x and g of x to each other, okay? And it's trying to see, as x approaches infinity here, is one of these functions going to grow much faster than the other, okay? Now, if both of these functions grow at what we call relatively the same rate, and to kind of give you an example of that, let's say 2x squared and 30x squared minus 2. These two functions, because they're both quadratic functions, are going to grow at relatively the same rate, okay? And whenever something like that happens, we know that the limit of the quotient of these two functions just differ by some real number, okay? So in this case, if we were to do the limit of 2x squared divided by the limit of 30x squared minus 2, that result would just end up being 1 over 15. And since 1 over 15 is a positive real number, that's all that really matters, okay? We know that these two functions grow at relatively the same rate. So we have that situation here, then we know that the improper integral of the big function and the little function will either both converge or diverge, okay? And so again, this specifically helps us out in this situation here, where we have the improper integral of the big function diverging, or the integral of the little function converging. And so we're going to see an example of, well, how do we know what the big function is? How do we know what the little function is? Okay. So this key tip for using comparison theorem, I give you an example here to kind of know what a big function is and what a little function is going to be. Okay. So for the portion of your integrand, which is the function that you're trying to basically integrate, that contains the discontinuity here, or the other problem, or the thing that's kind of making it an improper integral in the first place, we want to use this as our bigger or smaller function. And it really just kind of depends upon the situation that we have. So for instance, if we had this example here, then of course we know that this improper integral could be rewritten this way, where we have 1 over x times in parentheses 2 plus e raised to the negative x in parentheses there. All that as your integrand. Now, the thing that is making this particular thing improper, or this integral improper, of course, is this upper limit here. But notice that this 1 over x could possibly cause a problem as well. And so what I mean by a problem is that, if you remember, this special case integral converges because if we are looking at this way, this is like dx over x raised to the p, where p is equal to 1. And we know that we know that this particular special case integral converges only when p is greater than 1. Okay, so we know when p is less than or equal to 1, this is going to diverge. Okay, so what we do here is we have to now decide if 1 over x is going to be our big function or is it going to be our little function. Okay, so in looking at what we have here, we notice that 1 over x is less than 2 over x, which will end up being less than 2 plus e raised to the negative x over x. Okay, so in this case, notice that the function that was given to us is our big function, and the one that we extracted out that is causing the quote-unquote problem is the little function. And so note that since the little function diverges, that means that the big function is going to follow suit according to the direct comparison theorem. Okay, so here, this is one where we could have used a direct comparison theorem to do, but I used it so that you can kind of understand the difference in between big function and little function. Okay, so again, in this case, 1 over x is the little function, and this 2 plus e raised to the negative x, all that over x, is the big function. Okay, and so my point here is that sometimes we are going to be in situations where we're going to see something like what we've seen here for the f of x and the g of x, but the properties for this is going to switch. Okay, meaning that we may have a situation here. Again, I don't understand why that's doing that. We will have a situation here where this 1 over x, it was the smaller function, but now it is the big function. And this 2 plus e raised to the negative x, all that over x, was the big function, but now it's a smaller function. So it's going to have a relationship of something like this. In this case, because the big function diverges, we don't have that situation here for the direct comparison theorem. So notice that we don't have if big function diverges, because remember, this g of x here, that was little function. So here, if little function diverges, then we know that big one also diverges. But we have nothing here that says if little function converges, then we know that the big one's going to follow suit. We don't have anything like that. Okay, so because of that, we have this limit comparison test that's here to sort of give us another way of being able to look at things. And of course, the key to this is knowing that both of your functions grow at relatively the same rate, meaning that if we take the limit of the two functions as x approaches infinity, is going to equal some real number. Okay. All right. So let's sort of simplify all of this to get a summary of what it is that we're talking about, and then let's work through some examples here. Okay. All right. So to make this simple, we know that the direct comparison theorem, I'll write this here, The direct comparison theorem tells us that essentially, if we strip out all the conditions and all that, if the big function converges, then we know that if the integral of the big function converges, then the integral of the little one will also follow suit and converge. And if the integral of the little function converges, then it means that the integral of the big function will follow suit and also diverge. Okay. Now, if we don't meet one of those two conditions here, then what we have to consider is the limit comparison theorem. And the limit comparison theorem says that, well, let's suppose number one here, that we don't meet these two conditions here. Okay. Now, how will we know that? Let's suppose that our big function diverges, or that our little function, that the integral of the big function diverges, or that the integral of the little function converges. Okay. So here we take the limit as x approaches infinity of a big function over little function. And I wrote it like this, but this could really be the other way too, where we have little function over big function. And that ends up equaling some real number value L that is positive. Then either we know that both the big and little functions integrals will end up converging, or the big and little functions integrals will both end up diverging. Okay, so hence why we say the improper integral of the big function and the little function will both either converge or diverge. Okay, and if we have either this information here or this information here, then we'll be able to make that decision real easy. All right, so let's look at some examples. So for this first example here, note that we're asked to figure out what is going to be the definite integral of this function here. Yeah, and I have no idea why that's doing it. All right, so we have this situation here. We want to figure out what the integral of this is going to be if we can. Now, just looking at this, we're like, don't know if we're going to be able to do that one. So let's look and see if this particular function or this particular definite integral even has an answer that we can compute. Okay, so we rewrite our definite integral this way. And of course, I just put it like this just to give you another way to look at it. The main thing here is that if we think about what we know, and the thing is, we want to know whether this converges or diverges, right? So the thing that's kind of up in the air as far as being able to compare something is this secant squared. Okay, so here we could look at our integrand as 1 over x raised to the 3 over 2 times secant squared of x. And notice here that secant squared of x is going to be greater than 1 for values of x, it's greater than 0 to 1. Okay. Now, how do we know this? Well, we know it because of what the graph of secant squared looks like. Okay, and I'll sketch a quick graph for you right quick just to kind of give you some context to this. All right, so we are considering the graph of, and I'll just do secant here for now. So we know the graph of secant. Got these vertical asymptotes here at x equals negative pi over 2, x equals pi over 2, and the graph of secant is going to go something like that. Make it look a little bit more accurate, more so like this. Okay, so that's what the graph of secant x would look like. So for secant squared, It's going to pretty much have the same profile, and I'm just doing it in between these two asymptotes here because we're asked to look at everything from 0 to 1. And pi over 2 is approximately 1.57. Okay, so that's why I'm not, drawing secant and doing the little parabola looking thing down below the x-axis here and down below the x-axis there. Okay. Now for secant squared, notice that it's going to look something like this. Okay. In other words, it's going to get to a point where it starts to rise higher, faster. Okay. So my point here is that regardless of what you look at here, we know how secant squared is going to act. Much like secant, just going to rise higher, faster after some point. Usually they'll start that at about 1. So you'll have this and it'll kind of go like that. Okay. All right, so we see here, this is the corresponding point when x is equal to 1. And what we are essentially trying to find is this area under the curve here. Okay. So we see that the corresponding output of secant squared is going to be a value, if we're excluding 0 here and including all the numbers up to 1, it is going to be a value that's going to be higher than 1 because of that. Okay. Just by sheer nature of what the graph looks like. So now that we know that, here we know that if secant squared is going to be greater than or equal to 1 for all values of x that are greater than 0 up to 1, then if I multiply both sides of this inequality here by 1 over x raised to the 3 over 2, then what that does is it makes 1 over x raised to the 3 over 2 a function smaller than what was given to us to integrate in the first place. Okay, so here by the direct comparison theorem, and I'm saying that because now we have we got this smaller function here. Okay, so by the direct comparison theorem, if we don't know, but we're saying if this integral of the smaller function is divergent, then it means that the integral of the corresponding larger function will also follow suit and be divergent as well. Okay, so what we have to show, and that's what this WMS means, we must show that the smaller function is indeed divergent. Okay, the integral of the smaller function is indeed divergent. Now, before we do that, note here that, again, we do not want you to get the integral that we're working on mixed up with that special case one. Okay, so remember the special case integral, where we know when that improper integral is convergent, that is only when the upper limit is infinity and when p is greater than 1. Okay, both have to be true to meet that special case. If we don't have that special case, we can't use that fact. And of course, in this instance, you see that this particular improper integral does not meet that fact, does not meet both of those conditions here. The reason why this particular integral is improper is because if I plugged in 0 in for x, I would have 1 divided by 0 there. Okay, so we know that 0 is not in the domain of that function. So make a long story short here, so now that we need to evaluate this, we just do it like how we did in the part 2 and 3 videos. So since the lower limit is the limit that's where the discontinuity is located at, we will do the limit as a approaches that lower limit from the right. Okay, and we will take the definite integral of just 1 over x raised to the 3 halves, or x raised to the minus 3 halves. We'll take the antiderivative of that and evaluate it from a to 1. Okay, so that is what is being starting the process of being done here. we actually evaluate the improper integral, actually evaluate the antiderivative here, simplify everything here, write it into a form that's going to make it easy for us to actually apply the net change theorem, and then we plug in 1 where we see x minus plug in a where we see x, and then simplify as much as we can. And we see that this is the result that we have. And so now all we need to do is take the limit as a approaches 0 on the right of that result. Okay? So when we do that, of course, if I let a equal 0 here, then you see that we end up having something divided by 0, which in terms of limits goes to infinity. But infinity is not a real number, so we know that this particular improper integral diverges. And so remember that this is the integral of the smaller function, or the little function. So since the integral of the little or smaller function diverges, and that means that the integral of the corresponding larger one has to follow suit. Okay. All right. So let's look at this next example here. So for this next example, notice that this one actually does meet the condition of the special case. Okay. So I'll come down here and do this one. So I'm going to write it in terms of what we got here. So we do see here that this particular integral looks kind of close to what we have here. Now the only thing here is that we need to figure out what p is, and in this case, assuming that we ignore that minus 8 right there, we can say here that p is going to be a 1/2. Okay. So the point here is that since our function here looks very close to one of those special case ones, we need to see if the special case function is going to be the big function or the little function. Okay. And we're going to either use the direct comparison theorem or the limit comparison theorem to be able to figure out whether that particular integral converges or not. So we see here from v being 9 to infinity that 1 over square root of v minus 8 will be a function that has bigger y values than 1 over square root of v. Okay? And we know that because, of course, if v minus 8 is going to give me a smaller number than v, so that means I'm dividing 1 by a number that is less, which is going to make the pieces that I divide 1 by larger. Okay. Now, we also know that 1 divided by square root of v is just the same as 1 over v raised to the 1/2. So in this case, let's do some labeling here. We know that this is going to be our big function. This is, and the 1 over v raised to the 1/2 will be our small function. Okay, so here, since the special case goes with the small function, we need to use the case that if the small function diverges, if the integral of the small function diverges, then that means that the integral of the larger function will also follow suit and diverge. Okay, so here we look at this situation, and again say if this particular function is divergent, then the small one, then that means the bigger one will follow suit. Okay. Now, of course, we see here that since we compared our smaller function and its integral here to what we saw here, and that p is 1/2, we know that for all values of p that are less than or equal to 1, this particular improper integral diverges. Okay. So because of that, we also know that the improper integral of the bigger function, which is what we were initially asked, that will also diverge as well. Okay. All right, so let's look at the next example. All right, so for this particular improper integral here, we know that it's improper because, first off, if we were to take 0 and plug it in here and here, we would have something divided by 0 in the denominator. So by definition, that's going to make this improper. Now, with that being said, we need to figure out what is going to be the smaller function, what's going to be the bigger function here. Okay. Now, one of the things that we know is that if we look at this carefully, that let me write this up here, for values of t that are in between 0 and pi, we know that sine of t, this value is going to be in between 0 and 1. Okay, and I'm actually going to write it this way. Okay, and so just in case you forgot, we know that sine of 0 is 0. We know sine of pi over 2 is 1. And we know sine of pi is 0. So essentially, if you remember, our sine function kind of looks like this. And from here to here is from 0 to pi. Okay. So from 0 to pi, values of y go from 0 to 1. Okay. So we know that. So what this tells me is that if I look at this sine t here, the lowest this value is going to be is 0. The highest it's going to be is 1. Okay. And so since I can't include 0 here because technically I can't plug in 0 because it's not in the domain of that function here, we're assuming that sine of t is going to be greater than 0 when t is on this interval, which is the actual one that we're going to consider here. And actually, if we want to be really correct, it should be like this. Oh, sorry, not like that. Let me leave it like this. Yeah. Because here at pi, even though sine of pi is 0, we know if we stick in pi right here, that won't be 0, so we'll be okay. All right, so all of that is to basically say this. Okay, let's look at the highest case, and that is when sine is equal to pi, and I'm only doing this well, yeah. Let's look at when sine is pi over 2, okay? Because that's when it's going to be its highest value. So if I'm looking at it that way, then when I'm comparing here in the denominator is, I'm comparing these two functions, 1 over square root of t plus 0 and 1 over square root of t plus 1. Okay. Now, out of these two functions here, which one is going to have the larger corresponding y values for? Okay. And simply put here, we know that this 1 over square root of t will be larger than 1 over square root of t plus 1, just because of the fact that if the denominator is bigger, then that means that the total number itself is small. Okay. So this allows us to be able to pick our big function and our little function. Okay, and that's kind of where I've been trying to go with all of this. So I'm going to erase the rest of what I have here. And so what we're going to do here is we're going to say let f of x, which I'm going to call the big function. We're going to let that be 1 over square root of t. And we're going to let g of x, which is the little function, be what was given to us. Okay. So we have that. So since the big function looks like something that we may be able to deal with, then here we know from the direct comparison theorem that if our big function converges, then it means that our little function will also converge. Okay. So I'm going to go ahead and erase this as well. So I want to say here, therefore, from the direct comparison theorem, I'm just going to call it DCT here. If we know that the integral of 0 to pi of 1 over square root of t dt converges, this will imply that what we're asked to find out if it's going to converge or not will also converge as well. Okay, so what we must show is that this particular improper integral converges. Okay. Now, before we begin, note that if we're able to show that the integral that we've proposed, the integral of 1 over square root of t evaluated from 0 to pi, if that actually does end up converging, we'll be able to get a real number for this answer. And because of that, we can automatically say, without knowing exactly what it is, that this particular improper integral will also converge. Okay. If we find out that what we are proposing, what we want to show to converge actually diverges, then we're going to have to use the limit comparison theorem. So that means we're going to have a little bit more work to do and try to figure out if our actual improper integral that we're trying to figure out whether it converges or diverges, we're going to have to use that theorem to be able to do. Okay, so we hope that this works. If it doesn't, then of course we're going to have to employ the limit comparison theorem. Okay, all right, so let's go ahead and dig in and get this done here, since we've done a lot of talking to set it up. All right, so for here, if I'm going to do the integral of all this business here, which is just the same as t raised to the negative 1/2 dt, then if I take the antiderivative of that, that should end up being 2. Oh, sorry. Let's go ahead and write out the proper way to do this first. So we need to do limit as a approaches 0 from the right of, this will be a to pi t raised to the negative 1/2 dt. All right, and then from here we'll go ahead and take the antiderivative, and that will be 2u raised to the positive 1/2. Switch the way that this looks. And we'll evaluate that from a to pi. So this will just be limit as a approaches 0 from the right of 2 times, and this will just be square root of pi minus square root of a. All right. And so from here, if we keep on going, if we evaluate this at a, I don't need that there. If I go ahead and evaluate it at a, then I know that if I plug in a to be 0, this will just end up being 2 times square root of pi. And of course, square root of pi, 2 times square root of pi is a real number, and it is positive. So because of that, we know that this particular integral here is going to converge. And because this integral here converges, then we also know that this particular integral here that we were asked about converges as well. Okay, so the answer to this question is going to be yes, but it's going to be yes because we saw that the integral of this bigger function also converged. Okay. All right, so let's look at example D here. So I'm going to do some separation here for this one. All right, so we want to consider this improper integral of x raised to the -2 times e raised to the 1 over x dx, evaluated from 0 to natural log of 2. And we want to figure out whether this particular integral converges or diverges. So here there's actually a couple of different ways we could do this problem, but we want to go and do it the way with the path of least resistance. And so what that means is we want to not do so much calculation, but figure out if we have to use calculations or computations here, do the minimal amount. Now, I can just tell you just by looking at this that the longer way to do this problem is to kind of take the approach of this. And so I'm going to start writing it just to kind of give you an idea of how this looks. So let's say here we know that this is an improper integral here because the 0 can't be plugged in right here into the exponent 1 divided by x. Also can't be plugged in here for the x raised to the -2. We end up dividing by 0 in both cases there. So if we were going to evaluate this, of course, the problem area is at x equals 0, so we would have to say limit as a approaches 0 from the right of, and then we'll say a natural log of 2 of, and I'm just going to, I'll write it like this. So it'll look like this. And so this will be the integral that we have to evaluate, and then evaluate the limit of that result. Now, if we were going to do this the computational way, what you would do is something like this. You would say let u equal x raised to the -1. And of course, if you took the derivative of that, you would see that that ends up being a negative x raised to the -2 dx. And so what this would end up being here is when you rewrite everything, of course, you'll also let u of a actually be a raised to the -1. And you'll also have u of natural log of 2. This will be 1 over natural log of 2. Okay. So if you did all this, what this will end up being now, when you rewrite all this, and I'm going to do this in a different color here, you'll have limit as a approaches 0 from the right of integral basically 1 over a over 1 over natural log of 2, and you would have, if we were to actually work all this out, forgot to do that part, so let's do it here. So this would end up being a minus du is equal to x squared, x to the -2 dx. So because of that, this will be that integral of e to the u du, but because of this minus here, we would have a minus sign on the outside of that. And of course, we could flip that around by just basically flipping our limits of integration here. So this would be natural log of 2 like this, and this would be 1 over a. And this minus sign would go away. All right, so my point here is that if we did this, it looks like this is going to be a relatively simple integral to evaluate. And it will, because of the fact that e raised to the u, the antiderivative of that is just e raised to the u. But then we got all of the, 1 over a's and 1 over natural log of 2's to deal with afterwards. So that actually ends up being a little bit more computation than what we realize. Okay. So although we can do it this way, and you'll find out whether you go evaluate that definite integral and then do the limit of that result, you'll figure out whether it's going to converge or diverge just in your answer. Okay, so that's one approach. The approach that I want to use here is I want to use one of these theorems. I'm going to start off by using the direct comparison theorem to see if that works. If it doesn't, then I will use the limit comparison theorem to see if that works. Okay, so I'm going to erase what I have here, and then we're going to approach this problem as if we were trying to do it using the direct comparison theorem. All right, so now that I have that erased here, let's look at this another way. So let's look at this in this way. Okay, so I'm just writing it different because how we're going to look at our integrand to be able to get our big and our little function is going to be better if we write it this way. So notice here that we have 1 over x squared, and we have e raised to the 1 over x. Okay. Now, one of the things that we notice here is that the problem with this particular integrand is this function, and it's mainly because of the exponent here. Okay, so what we want to do is we want to consider the function 1 over x squared, and we also want to consider the original function that was given to us in our integrand, which would be e raised to the 1 over x squared. So why do we want to consider these two functions? Okay, well, we want to consider them because, of course, one of the functions that we need to use to compare in the comparison theorem needs to be the actual function that was in the integrand. The other one that we need to consider is one that will be relatively easy for us to either show or state that the same integrand, well, the same limits of integration, but with the other function that we're using to compare it with, that particular improper integral will either converge or diverge. Okay. So, like I said before, the problem is the 1 over x in the e raised to the 1 over x function. Okay. So we know that. So that's also going to be the function that we look at to be able to compare to see whether 1 over x squared or e raised to the 1 over x divided by x squared is a bigger function. Okay. So if we think about what's going on here, and not to make this real convoluted, but I'm not. We know that e raised to the anything is going to be a function that has to lie strictly above the x-axis. Okay, so by definition, since e raised to the 1 over x is going to have to be greater than 0 here, then I also know that this particular function, the 1 over e raised to the x divided by x squared here, is potentially going to be bigger than this one. Okay. Now, how will I actually know that? Well, I'll actually know that once I investigate this a little bit further here. Okay. Now, notice that we are considering values in between 0 and natural log of 2. Okay. So on this particular interval here, so I'm just going to write this. Note that on this interval from 0 to natural log of 2, this implies that e raised to the 1 over x, we're going to have values that are in between. And if we take 0 here and plug it in, so we know that this will end up being e raised to the infinity, because, of course, 1 divided by 0 here, if we look at it limit-wise, goes to infinity. So we know on the high end, that's going to be infinity. Okay. Now, the question is what is it on the low end? Well, on the low end, we have e to the 1 over natural log of 2. Okay. And I'm going to erase this part here, move it up. Okay. So we have this, and notice here that e raised to the 1 over natural log of 2, where that 1 over natural log of 2 is in the exponent. This is actually an expression, oops, I don't know why that pen does that. This expression here is actually bigger than e raised to the 0 over natural log of 2, okay, which you know that equals 1. So we may not know exactly what 1 divided by a natural log of 2 actually is, but we know whatever it is bigger than 0 divided by natural log of 2. And thus, we know that this e raised to the 1 divided by natural log of 2 is actually a value that is higher than 1. Okay. So here what I'm going to say is I'm going to put a 1 here, parenthesis there, and since technically we can't include the 0 here, this parenthesis makes sense. Okay. Now, of course, for the natural log of 2 part, we could include that. So here I am going to go ahead and put a parenthesis here because of the fact that, remember that e raised to the 0 is essentially equal to 1. Okay, so all of this is equal to 1, but this 1 over natural log of 2 should be greater than that. Okay, so that means there's a corresponding value of x here that is, a corresponding value here in between 0 and 1 is going to match up to that. Okay, which means that the corresponding output for this is going to be greater than 1 again. Okay, so I'm getting to all this to basically say that whatever this particular value is, when I compare it to 1 over x squared, this is going to be the bigger function for all values of x that I'm considering from 0 to natural log of 2. Okay, and so that is how I know that the function that I was given is the bigger function, and the one that I extracted out of it that was simpler to deal with is the smaller. So since I have the small function here, what I have to do is I need to show via the direct comparison theorem, I need to show that this particular integral here will diverge. Okay. Now, again, why do I need to do that? Remember, when we use the direct comparison theorem, remember that if the integral of the bigger function converges, then that means that the integral of the smaller one will converge. Okay, this is the bigger function, and we don't necessarily want to evaluate the integral of that, because remember, I'm using this, I'm trying to use the direct comparison theorem to do it. So here I have to rely on the small function, and according to the direct comparison theorem, if I'm using the smaller function in the integrand, then that means that if the integral of the smaller function diverges, then that means that the integral of the corresponding larger one will also diverge as well. Okay, so I know this seems like it takes a lot longer than doing it the other way, but in practice, this is actually shorter if you can kind of look at these functions and figure out, hey, what's bigger or what's small. Okay, so there's a little bit more thinking involved here, but if you think first, there's less actual work to write. If you would have did it the first way we were considering, there would have been less thinking, more work. Okay. All right, so now all of this that we've talked about here, we sort of set the foundation to basically say we need to figure out what this is going to be. Okay. Are we actually going to get a real number value for what I've circled or not? And so we're going to go ahead and work on that and actually see. So if we evaluate this integral, I'm going to write it like this now. This will be much more simple than what we were trying to do earlier, because we won't need the substitution rule to be able to do it. Okay. Since again, the 0 is our problem, we're going to rewrite this as limit as a approaches 0 from the right of integral from a to natural log of 2. And this will be just x raised to the negative 2 dx. And if we were to take the antiderivative of x raised to the negative 2, that would end up being a negative x raised to the negative 1. And that will be from a to natural log of 2. And negative x raised to the negative 1, That's just a fancy way of saying a negative 1 over x. Okay. So here we have limit as a approach 0 from the right of a minus 1 over natural log of 2 minus a negative 1 over a, which this minus a negative here will just end up being addition. Of course, if you're looking here at this point, we just need to plug in 0 for a. And in that second term, you're going to see that we have a problem. Mainly that we end up having 1 over 0. And of course, in terms of limits, this is going to give us this negative 1 over natural log of 2 plus infinity, which makes all this go to infinity. So what this tells us is that our integral diverges. Okay? And so since this integral diverges, then that means that the corresponding integral that we were asked to deal with in the beginning also diverges. Okay? So here we would say, therefore, integral from here to here of x raised to the negative 2 times e raised to the 1 over x dx diverges. And again, this communicates to us that there is no way, whether we use human or computer, that we're going to be able to evaluate the area under the curve of that particular function from this particular function here, from 0 to natural log of 2, and actually get an answer for the area under the curve. Okay. All right, so this will conclude this particular video. I have one more video that I need to do in this series, because now that we've kind of compiled all this information together about what an improper integral is, what it is not, being able to look at integrals and evaluate them to determine whether they converge or not, knowing if they converge, knowing that the improper integral converges and evaluating it, and now using the direct and limit comparison theorems, we need to get some more practice with being able to use both the direct comparison theorem and the limit comparison theorem, so that we can see when we need to use one and not the other. And so with that, this last video that I'm going to do is going to go over examples of those types of situations. So, and we'll start out most of these problems where we'll try to either use the direct comparison theorem or the limit comparison theorem to get started, and then we'll just kind of take it from there. The only exception to that will be if we see something that looks very similar to the special case type of integral that we saw, and if we see something that looks like that, then of course we can make an assumption on whether it converges or diverges just based upon those conditions. So anyway, I'll see you in the next video so that we can close this out.